Go.
My opera voice. Right. Ready?
Yeah.
Right. My name is Garrett Murray. I'm a graduating senior at San Jose State University.
I'm Carolyn Frill. I'm also a graduating senior in the Materials Engineering Department.
And we've collaborated with Jabil to produce an internally cooled surgical bone drill bit to reduce the onset of osteonecrosis. Now, one of the reasons why we're interested in reducing the onset of osteonecrosis is because it causes patient bone tissue to actually degrade over time. This isn't immediately identifiable during the operation or immediately after. It actually takes several weeks to occur. And when this happens, sometimes it causes a fixture that could be placed inside the body to actually become detached from the patient's bone. For example, if surgeons are placing a fixture on a patient's femur to try to heal a broken bone, then they will fasten oftentimes a piece of metal to keep the bone together and allow it to heal. With the fasteners that they use that drill into the bone, they could cause onset of osteonecrosis and then cause the fixtures to remove themselves from the bone, ultimately rendering the whole fixation device to actually become detached and no longer be of use to the patient, not helping them recover any faster. When that occurs, surgeons will have to go back and replace that, often drilling even larger holes inside of the patient, again causing more pain, damage, and extreme costs due to having to, again, re-perform the surgery. And so when we originally sought after creating this device, one of our biomedical motivations was to take into account the emerging market of surgical devices. In particular, the robotic surgery devices such as the Da Vinci and many others that are coming to market.
Get closer.
We're expecting an extremely large amount of these robotic surgery devices, those being assistive surgery and even automated surgery, to reach the market. So we want to make sure that we could take a currently used technology, something that hasn't been innovated in a very long time, and bring it up to current technology and really leverage off of what the new technology has to offer. For example, with the Da Vinci robot, it's able to monitor the temperature at the drilling site. It could even monitor the rate in which the surgeon is drilling into the patient. We think we could leverage off of this technology to understand how much fluid is being pumped into the patient, possibly how much fluid is being pumped into our drill bit to better maintain the temperature at the interface between the drill bit and the patient's bone, ultimately to reduce osteonecrosis. We did have our FDA considerations. A bone drill bit is a Class 1 medical device. We consider this to apply to our product as well, since it is not impacting the workflow of the surgeon in any way by using this device compared to an old surgical drill bit. Our materials, we use the M290, the EOS M290 M290 SLS metal printer. And then we're also using that to create 4 different prototypes. As you can see here, we actually have all of our samples here. We created 4 prototypes, one with a circular inner channel, another one with a mechanically optimized channel, another with a more of an organic shape, and then we also have one that has a star design. So in this project, we wanted to make sure that we designed a bit. We wanted to model an ANSYS to make sure that we could actually test the efficiency of the bit before having to manufacture it, considering that metal 3D printing is a very expensive process. Then we have our bit manufacturing, where we actually print the metal drill bit and also do some post-processing. We have our benchtop test, which we're going to do to verify the results of the ANSYS test, just to make sure that the ANSYS results are aligning with what would occur in reality. And then finally, we did some materials characterization to understand whether or not this manufacturing process is feasible for a product like this, and whether this project should continue. So our design, you can see 4 designs here. This is our circular design, the maximized design, the mechanically optimized or the organic shape, and then we also have the star bit design. Ultimately, we only ended up testing the circular and maximized design. In our ANSYS results, we actually set up the experiment where we were using a hot bath to simulate the heat generation at the tip of the drill bit. So we set the hot bath to 55 degrees Celsius, and we have the coolant, which is running inside of the drill bit through its internal channels. We have that set to 7 degrees Celsius. And so that's simulating almost like a ice water temperature. So we actually ran the test. We measured temperatures just under the surface of the tip of the drill bit. We measured the outlet temperature, and we also measured the inlet temperature. We found that in our simulation, we actually were able to reduce the operating temperature from 55 degrees Celsius all the way down to our best result of 39 degrees Celsius, with a 16 degrees Celsius reduction in temperature, which is very significant since it actually brought us down from above the critical point of osteonecrosis to far below. The critical point being 47 degrees Celsius, we're able to drop a temperature of 55 all the way down to 39. Excellent results that we didn't expect. In terms of manufacturing, again, we just used the EOS M290 printing machine to actually create these products. In our benchtop test, we verified the results in our ANSYS model, where we were able to measure the inlet and outlet temperatures. We're unable to measure inside the tip of the drill bit, but we confirmed that if we are able to get similar results in the inlet and outlet temperature, then we could safely consider that the tip temperature is going to match in reload. So in our benchtop test, we simulated that test that we ran in ANSYS, where we had the tip of the drill bit dipped into a hot bath of 55 degrees Celsius. We ran a 7-degree Celsius coolant through the drill bit, and then we actually got these results. Our results varied by about 21 to 30%, so that's the max temperature and lowest temperature of our inlet and outlet temperature, being about 20 to 30 degrees off of the Fluent model. We actually find that in reality this would actually cool the bit from 55 degrees Celsius down below about maybe 12 degrees Celsius. So this would effectively cool the drill bit to about 42 degrees Celsius, which is, again, under that 47 degrees Celsius critical temperature that we're trying to avoid. Now, Tara-Lynn will actually explain some of our material characterization and whether or not this product could actually be manufactured.
All right. So one of the concerns with using 3D printed steel to make a drill bit is, are there any sort of characteristics about 3D printed steel that would make it a bad candidate for a drill material? So one of the concerns was that it's going to have any sort of internal flaws or anisotropy, because during printing, then it prints a layer and then it fuses it together and prints another layer on top of that and another layer on top of that. Because of this anisotropic processing, then it's possible that the end result is going to have anisotropy in its properties. So, in order to test this, then we sectioned and polished a few samples of the 316L steel that had been printed and investigated its structure. We found that the edge of the 316L steel print is actually still quite rough, and on the outside of the drill that's not going to matter because post-processing can polish that down to a very nice sheen, but on the inside where the drill bit channels are, then those can't be accessed, so they'll be rough during the entire operation of the drill bit. The more concerning property, though, is that the presence of many tiny microvoids throughout the material. And these microvoids are actually a characteristic of 3D printed steel in that small gaps form between the metal particles as they're being sintered together. This means that these tiny holes cannot actually be removed and are going to be a permanent feature inside the drill bits. So just to see if this anisotropy is actually going to be bad for it, then we ran a few Rockwell hardness B tests on it, and we found out that in the print direction it's actually slightly softer, as a 92.5 Rockwell hardness B and a 93 for the X and the Y directions. But this is a difference of less than 1%, so even though there is anisotropy present, it's not going to have any sort of effect on the mechanical properties of the drill bit itself.
So in conclusion with this project, we were able to successfully design a internally cooled orthopedic drill bit. We were able to manufacture it with using the EOS M290 printing, and then we were able to test it in ANSYS and actually verify that those results were fairly accurate, 21% being a fairly accurate test. We were actually able to drill into bone with these drill bits, and we found that it drilled in very easily, no excess swarf being stuck in the drill bits, and we really think this would be a great project to continue pursuing here at Jabil, and we really think it could be a great product. Thank you.